Okay, 3.6, proof by contradiction. So a proof by contradiction. Okay, also called an indirect proof. Okay, is we assume the theorem is false. And we seek a contradiction. Okay, we assume the conclusion is false and then we seek a contradiction. Okay, it's kind of like a proof by contrapositive, but we're just uh uh if we find a contradiction, then we know that the original had to be true. Okay, therefore the theorem, or we'll say the original theorem, must be true. So example 1. Okay, prove the theorem by contradiction. Okay, the theorem is for every pair of positive real numbers A and B, the square root of A plus the square root of B is not the same as the square root of A plus B. Okay, those are not equal. We want to prove that those are not equal. Okay, so we're going to assume the opposite. We're going to assume that they are equal. Okay, so proof. Assume the opposite and seek a contradiction. Assume the opposite of the conclusion. The conclusion is true. We're going to assume that it's the conclusion, the opposite of the conclusion is true. So we're going to say that the square root of A plus the square root of B equals the square root of A plus B. Okay, squaring both sides gives the square root of A squared plus 2 times the square root of A square root of B plus the square root of B squared equals A plus B. We get A plus 2 times the square root of AB plus B is equal to A plus B. If I subtract off A and I subtract off B, I get 2 times radical AB equals 0. If we divide by 2, we get the square root of AB is equal to 0. Huh. Okay. This is only true if A equals 0, B equals 0, or both A and B equals 0. Okay. However, this contradicts that these are positive real numbers. Okay. So if it only works for 0, that where they're equal, then it's not going to work for numbers that are above 0. So therefore, this contradicts the hypothesis that A and B are positive real numbers, and therefore the theorem that if A and B are positive real numbers, I'm just going to go are positive. I'm tired of writing positive real numbers. Are that if A and B are elements, I could say A and B are elements of R positive. Use a little notation here. Then the square root of A plus the square root of B is not equal to the square root of A plus B. Okay, and thus we have proven that to be true. Okay. A proof by contrapositive is a special case of proof by contradiction. We assume the opposite. Of P implies Q. Okay, or not P implies Q. Then we can say not P implies Q is logically equivalent to not P or Q. Is that and or? It's or. Okay, not P or Q. Okay, turning the conditional statement into a logical one with a proposition. Okay, so by De Morgan's laws, this thing is equal to not P and not Q, which is logically equivalent to P and not Q. Okay, so we're assuming the hypothesis is true, but we're getting the conclusion, okay, as false. Okay, we're assuming the hypothesis is true, but we're getting a false conclusion because we assumed that the theorem, the opposite of the theorem. Okay. Okay, to show that it's not Q implies not P, which is the contrapositive proof. Okay. We would do not Q. Okay. Or not P. Okay. So we just not the first one and then keep the second one. Okay. To change it from a conditional statement into a proposition. Okay. Simplifying this, we're going to do the reverse of De Morgan's law. I think, yes, we're going to do the reverse of De Morgan's law. We're going to factor out a not here. This gives me not Q and P. Okay, is logically equivalent to not P and not Q. That's just commutativity. Okay, which is the conclusion that we're looking for. Okay, this is the conclusion. Okay. So it's that we have the hypothesis P and not Q. Okay. If we get a contradiction there, then the opposite must be true. Thus, the assumption not P implies Q is false. If, okay, that's false. If not Q implies okay, if not Q implies not P is true. Therefore, okay, P implies Q is true by contradiction. Okay, so that kind of just runs through the logic of, why does contradiction work? You assume the opposite and seek a contradiction. And if you get a contradiction, something that doesn't work, it contradicts the original hypothesis, then you know that the original statement had to be true. Okay, so we kind of went through the logic here of why that stands up. Why is that the case? Okay, let's do a second example. Okay, example 2. Okay, prove the theorem by contradiction. Okay, prove the theorem by contradiction. Theorem. Okay, the square root of 2 is irrational. Okay, so what would we want to do here to prove this by contradiction? What would we assume? Okay, we want to assume the opposite, yeah, and seek a contradiction. So we would assume radical 2 is rational. Okay. Okay, so we know that then radical 2 can be expressed as a ratio of two numbers, a over b. Okay, if we square both sides, Then we get 2 is equal to a squared over b squared. And if we multiply both sides by b squared, we get a squared is equal to 2b squared. Okay. Thus, a squared is even. Okay, since okay, uh, it is twice the square of an integer. Okay, so it's divisible by 2. Okay, if a squared is even, okay, okay, if a squared is even, then a must be even as well. Okay, why is that? Why? Let's think about that for a second. If a squared is even, then a must be even as well. Why is that true? Mhm. Well, we kind of do this by exhaustion. If a squared is even, let's see, then a squared equals 2m okay, then why must a be even? Did we prove that by contradiction? I feel like we proved something about even and odd. Okay, in the previous. Okay, if for every integer n, if n squared is odd, then n is odd. We kind of proved the contrapositive though of that. It's that if if n is even, then n squared is even. So that's a proof from section 3.5. Okay, we went through the proof. This is, again, we can use things that we previously proved. In section 3.5. Okay, proof from the proof by contrapositive. Okay, proof by contrapositive. Okay, we said assume n is an even integer, and then we squared those things, and we found that n squared had to also be even. Okay. Okay. So if a squared is even, then a must be even as well. Previously proven. Okay. Okay. Since a is even, then a must be equal to 2k for some integer k. Okay, using a squared equals 2b squared, we can say that okay, we can plug 2k in for a. So 2k squared equals 2b squared. This is 4k squared equals 2b squared divided by 2. We get b squared equals to 2k squared. So therefore, b squared must also be even. Okay, so if a is even, then a squared is even, and then b squared must be even. So therefore, b must be even. And thus, b must also be even. Okay, if the squares are even, then the original ones are even. Okay. Okay, we could kind of go to an aside on this and be like, okay, if I take an even times an even, okay, and I square an even number, if I take an even number, which is 2k, and I multiply it by itself, that's going to give me 4k squared, which is 2 times k squared, 2 times 2k squared, which again is an even number. So if you multiply an even times an even, you get an even. Okay, even times even, or even squared. Okay, is an even number. What if we did an odd times an odd? What would you get? Okay, well, an odd is 2k plus 1. I feel like we did this already before as well. 2k plus 1, which is 4k squared plus 4k plus 1, which is 2 times 2k squared plus 2k plus 1, which is again an odd number. So again, all of these facts have been previously proven. An even squared is equal to an even, and an odd squared is equal to an odd. Okay, so we know now that A and B must be even. Okay, so A and B must both be even. Okay, if their squares are themselves even. Okay, since A and B are both even, and therefore contain a factor of 2, okay, so, okay, so if A is an even number, it's 2 times some value. We'll call it K. If B is an even number, it's 2 times some value, we'll call it M. And therefore, A over B is not in lowest terms. It's not the smallest value. Okay. Okay. It's saying that then radical 2 is equal to some 2k over 2m. And you can keep using this logic to say, well, we're never really going to get, right? We're never going to really get a value, because if we can keep thinking of this as 2 over 2 and we cancel, we get k over m, but then we can go back again and say, well, k had to be even and m had to be even. Then we would keep going, you keep dividing by 2 infinitely. Okay. And so you're just, so you keep reducing infinitely. And this contradicts that radical 2 is rational. It's only rational if you can get a value, one even value over an even value. But once you cancel those 2's out, you can get 2 more and 2 more and 2 more and 2 more and just go on forever. So the only way that this thing is rational is if you say that it's forever an even number over an even number, which can't be true, right? Okay, so this contradicts our assumptions, and therefore the original statement that radical 2 is irrational must be the case. Or we could just say just must be true. Okay, when you've eliminated everything else and proved that everything else is false, then what's left over must be true. Okay, and a proof. Okay.